Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 12, the Gullstrand equations and cardinal points. So, this is a rather dry topic, and that's because our optical systems are generally surrounded by air. They're not in water. So, Alvar Gullstrand was a Swedish doctor and also a mathematician who came up with the equations that described the optics of a thick lens, or the optics of an optical system in which there was more than one thin lens. And then he used these equations to then describe the optics of the eye. And for that, he received the Nobel Prize in Physiology or Medicine in 1911. So, to calculate the equivalent power of two thin lenses or one thick lens, he came up with the equation Fe equals F1 plus F2 minus C F1 F2. So big Fe is the equivalent power of this optical system or this thick lens. F1 is the power of the front surface if you have a thick lens, or the power of the first thin lens if you have two thin lenses. F2 is the power of the second surface of a thick lens, or the power of the second thin lens. C is the lens thickness in meters divided by the index of the thick lens, or just the distance between the lenses, thin lenses, if they are in air. So here's an example of two thin lenses. We'll make them convex, although they don't have to be. And the first lens has power F1, and the second lens has the power F2. And the distance between them is C, which in this case is just the distance between them in meters if they are surrounded by air. And remember that C must be in meters. On the other hand, if you have a thick lens, in this case, F1 is the power of the first surface. If it's surrounded by air, N is the index of the lens material. And F2 is the power of the second surface. And the thickness of the lens is D, and D divided by N equals C in the formula. Now, there are 6 cardinal points in an optical system. The optical system does not have to be Catholic in order to have cardinal points. It can be any religion you want. It can even be an atheist optical system. So the first 2 cardinal points are the primary and secondary focal points. We've spent a lot of time on those points in previous units. We're not going to spend a whole lot more time on them in this unit. Then we have the primary and secondary nodal points, abbreviated capital N and capital N prime. And we have the primary and secondary principal points, abbreviated capital H and capital H prime. You might think that they should be abbreviated capital P and capital P prime. There are some optical formulas that use P as the power of a lens. I don't, but others do, and that would probably confuse people. So the German word for principal point starts with H, and that's where the H comes from, I believe. So if you look at this thick lens, the incoming ray and outgoing ray have the same tilt, the same slope. If you extend the incoming ray forward and the outgoing ray back, where those extensions hit the optical axis. That's capital N on the left and capital N prime on the right, the primary and secondary nodal points. The refracted ray passes through the optical center of the lens. If you recall thin lenses, when a ray was sent through the optical center of the thin lens, it was undeviated. So this is the same principle. A ray that's refracted through the optical center of a thick lens is also undeviated. Now, the principal planes are hypothetical areas where all refraction takes place. Also, the head administrator of a public school, if he or she owns a jet, that is also a principal plane. But I digress. The principal points are where the principal planes cross the optical axis. So in our thick lens on the left here, we're sending in a ray from the primary focal point. It is refracted parallel to the optical axis. And if we extend forward the path of the incoming ray and extend back the path of the outgoing ray, where they meet at the primary principal plane. If we sent in other rays from F, they would all meet at this primary principal plane. And where it crosses the optical axis, that is the primary principal point, or capital H. On the thick lens on the right, we're sending an ray from infinity. It's parallel to the optical axis. It's refracted through the secondary focal point F prime. We extend forward the path of the incoming ray and extend back the path of the outgoing ray. They meet at the secondary principal plane. If we sent in other parallel rays, they would all meet at the same plane. And where the secondary principal plane crosses the optical axis, that is the secondary principal point, or H prime. Now, if we removed the thick lens on the left and replaced it with a thin lens of the same power where H is, and if we removed the thick lens on the right and replaced it with a thin lens of the same power where H prime is, the paths of the rays would match the paths of the rays on the top, because all the refraction takes place at these thin lenses. Now, life gets easier if the optical system is surrounded by the same medium, which they usually are. They're usually surrounded by air. So in that case, H and N coincide, and H prime and N prime coincide. The primary principal point and nodal point are in the same place. The secondary principal point and nodal point are in the same place. Now I've added H and H prime, F and F prime, and the object M and the image M prime to our diagram. When dealing with thin lenses, you recall that the object distance was measured from the lens surface to the object. When you have a thick lens, that object distance is measured from the primary principal point to the object. Similarly, the image distance for a thick lens is measured from the secondary principal point to the image. The primary focal length is measured from the primary focal point to the primary principal point. And the secondary focal length is measured from the secondary focal point to the secondary principal point. Okay, with a thin lens, the principal points corresponded to the location of the thin lens. When you have a thick lens, that's not the case. And so these measurements must be made with respect to the principal points. Some people say studying about cardinal points is for the birds. I disagree. So I'm going to show you the approximate locations of the principal planes in these 6 thick lenses. From left to right, we have a plano-convex, a biconvex, a convex meniscus, a concave meniscus, a plano-concave, and a biconcave lens. So we have our primary and secondary principal planes, approximate locations. The important thing to notice is that the principal plane does not necessarily have to be inside the lens. It can be outside the lens. So when you calculate the locations of your principal planes, as I'll show you shortly, don't be surprised if you find that they are not inside the lens itself. This ruler tool doesn't let me draw a line any place where I want to. Let's move it over just a little bit. And we'll label them H and H prime for the primary and secondary principal planes. The back vertex power of a thick lens is the power of a thin lens placed where the back surface of that thick lens used to be. And that's important in the real world when you're dealing with spectacle lenses. If you have a thick spectacle lens, you don't know where the principal planes and the principal points are, but you do know where the back surface of the lens is. And you can use that actual physical location then to know what the distance is to the focal point on the same side. That's called the back focal length. So the back vertex power formula is equal to F over 1 minus CF1. So F is the equivalent power of the thick lens. That's the power with respect to the principal plane. F1 is the front surface power of the thick lens. C is the thickness of the lens in meters divided by the index of refraction of the lens, N. And F prime V is the back vertex power. So when you measure the power of a spectacle lens, you are actually measuring the back vertex power. That's the reading that's displayed in the electronic lensometer. It's the reading that you read off the dial if you use the manual lensometer. So we're going to learn how to locate where the primary and secondary principal points are. I have here a thick lens. The same formulas can be used for 2 thin lenses located at A1 and A2, which in the diagram are the front and back surfaces of the thick lens. We've also drawn in their centers of curvature, C1 and C2, and the principal planes H and H prime. So here are the formulas for calculating the locations of the principal points. The distance from the first surface of the thick lens or the thin lens to the primary principal point equals minus CF n minus 1 over R2 if you're given the radii of curvature, or it equals CF2 over F if you're given the powers. A2H prime, the distance from the second surface to the secondary principal point in the thick lens, or the distance from the second thin lens to the secondary principal point, equals minus CF times n minus 1 over R1 if you're given the radii of curvature, or it equals minus CF1 over F if you're given the powers of the surfaces and or the powers of the two thin lenses. Now, when you're using the first mathematical expression after the first equal signs, where you're plugging into the radius of curvature, all the units can be whatever you want them to be as long as they all match. They can all be meters, centimeters, inches, miles, whatever makes you happy. For the last set of mathematical expressions after the second equal sign, where you're using the powers, C must be in meters. And the reason for that is the powers are given in diopters. The diopter is 1 over the focal length in meters. So meters are inherently in that mathematical expression, and C must be in meters. So n is the index of the thick lens. If you're dealing with two thin lenses, n is 1 because they're separated by air. F is the equivalent power of the thick lens or of the lens system when you have two thin lenses. F1 is the front power of the thick lens or the power of the first thin lens. F2 is the back power of the thick lens or the power of the second thin lens. R1 is the first radius of curvature, the distance from A1 to C1, which in this diagram goes from left to right and would be a positive number. R2 equals the second surface's radius of curvature. That equals A2C2, which in the diagram for a biconvex lens goes from right to left and would be a negative number. C equals D over N. D is the thickness of the lens if you're dealing with a thick lens, or it's the distance between the two thin lenses if you're dealing with that type of system. And remember, C is in meters for the last mathematical expression, CF2 over F and minus CF1 over F. And the focal length equals 1 divided by the power.